Okay, let's get started. Last time we were here, right? Arm is providing multiple data transfer instructions. This one set of instructions. Okay, store and load multiple instructions, and Arm is providing another set of instructions called FA, EA, ED, and so on. Okay, second set of instructions. Good news is, that instruction, STMFA, is functionally equivalent. Same actually, it is same as this one, IB. Okay? EA, second row, right? STMEA is equal to this one, and this one equal to this one, and so on. Okay, and why? Then the question is why? Why Arm is providing this second set of instruction to make your life easier. The thing is, for stack operation, Arm is recommending you to use second set of instruction because that is more intuitive. So let me explain stack first. We have CPU and memory, right? Stack is simply memory area you reserved. Okay, so I'm going to reserve this memory area starting from 0. Okay, so 1 kilobyte, for example, 1 kilobyte memory. I'm going to use this one as a stack. Okay, you have to make that decision when you write program. Okay, and what is a stack? Stack is used to backup data in registers. For example, these 3 registers, right? R5, 6, R7. Backup these registers to the stack. Okay, backup. Because you have only how many? 16, 16 registers. Only 16, right? So once you have data loaded in register file, probably you want to do some processing with ALU. So after finishing data processing, you want to backup. Why? To make room for another set of data for data processing. Okay, so you load data, do some data processing, backup. Okay, load another data to something because you have only 16 registers. Very small number of registers. Okay, so backup. Okay, and sometimes you want to restore, right? You backup data in register. You want to restore. So that backup operation is called push. You are pushing this data to the stack, and restore operation is called pop. You are popping this data, the backed up data, to registers. Okay, push and pop. Okay, push and pop. So that is temporary storage, temporary area for backing up and restoring data. Okay, so when you push, okay, starting from zero, typically stack is, you say when you push data, then you say stack is growing. Okay, that is a stack, and you are pushing R7, 6, 5, 1, 2, 3, using a multiple data transfer instruction, LDM. Okay, and you know the rule, right? Rule is low, high, right? The low memory location is corresponding to low register number. High memory location corresponding to high register number. So starting from 0, address is incrementing like this. So when you back up, data should be stored like this. 1, 2, 3. Because stack starts from here, right here, this place, that place. Stack starts from this place. As you push data, and stack is growing. Stack is growing downwards. Growing downwards. When you pop, okay, when you pop, stack is shrinking, right? Stack is shrinking, right? So it is growing downwards as you push. So by default, when you push, okay. So then what do you have to do? What do you have to do? Push data. We use R13 register. So different name of R13 is stack pointer, right? R13 is stack pointer, and stack is used all the time when you run, high level code, C code, Java, you name it, right? When you run your high level code, that's stack. This push and pop operation happens all the time. Okay, so that is why CPU vendor reserve one register for stack operation. In ARM case, in ARM CPU, we use R13 as a stack pointer. So before you use stack, you have to initialize that R13 stack pointer register with some value, some memory location. Okay, so we want to initialize. So there are some ways to initialize R13. Okay, so stack is starting from this place, starting from this place, okay. Stack is starting from this place, okay, this place. Then probably by convention, you initialize a stack pointer to point 1 byte above that actual stack area. Okay, so that location. Okay, let's assume this location. So 1 kilobyte. So 1 kilobyte. 1 kilobyte is what in hex? 3 starting from 0. The last one is 3F. Right? That is the last address. 0, 3FF. 1 kilobyte. Okay, and we are talking about 4 byte data. So 3FC, and this one one word above, that is 400, right? So 1 kilobyte. Why 1 kilobyte? To the power of 10. If all 10 bits are 1, then you are talking about the last byte in this 1 kilobyte stack. Okay, 10 is what? If I write binary number 0011 1111, 10 ones, right? So 3 F and F. Okay, and we are talking about 4 byte, one word, 4 byte. So address should be 3FC. Okay, and one above should be 400. If you add 1, that means 100. So that is 400. So we initialize stack pointer to 400 like this. Then that is pointing 1 byte above actual stack area. Does it make sense? So far, so good. Any questions so far? Okay. So then, so that is typically used, right? Stack pointer initialized with the location 1 byte above the actual stack area. Okay. So when you push the data, what do you have to do? You have to decrement, right? That is not stack area, right? this location. That location is not, stack area. Stack area starts from 1 byte below. 1 byte below the location stack pointer is pointing, right? So you have to decrement to push data to back up some data. You have to decrement stack pointer first, because the location is you can say location is full. The location stack pointer is pointing. You can say it is full. Okay, so occupied. Okay, so you have to push data, you have to decrement it. Okay, decrement the stack pointer by 4, then store. Okay, to push data, so ARM is recommending STM, store multiple. Then in this case, right, stack is full. F means full. Again, the location is the stack pointer is pointing is full. This is not actual stack area. Okay, so you have to decrement it. Full and stack is growing downwards, descending. Okay, to push data, you have to decrement, right? Decrement by 4, then store. I'm trying to explain the meaning of this acronym, full descending, right? That full descending, okay, FD. Okay, trying to explain that. What does that mean? Full, again, the location is full. Location is already occupied, occupied by data, or it is not a stack area in this case, right? So you have to decrement stack pointer by 4, then push, okay? And then when you push, descending, stack is growing downwards, full descending. As you push data, stack is growing downwards, right? Address is 0 and incrementing upwards. Okay? STM-FD. Okay? Then when you pop, okay, then you push it, this data, and then you can load new set of data into R5 to R7. Okay, new data. Okay, because you backed up those data. Okay, you get new data and then do some data processing. So you are done. Okay, you load here new data and do data processing. Okay, then at the end, probably you want to restore the data. Okay, restore. Then you have to use LDM, load multiple, right? Load multiple. Then which one do you have to use? The rule is if you use FD when you push, you can use the same thing, FD. You have to use the same suffix. Okay, when you restore, use the same suffix. Stack is full, so you have to use FD. That is the rule. So it is easy. So what is easy? If you use STM for push operation, when you pop, use same suffix, FD, same suffix. Okay. So let me use. So what is this instruction? That instruction is what? Hold on. Okay, FD instruction. If you want to use one of these, then which instruction is corresponding to FD? FD. Think about this. Store multiple, right? STM, the location. This is not the location. You have to store data too, right? So what do you have to do? Decrement, what? Decrement before, right? Decrement is the register. Decrement before you store data, right? DB. Decrement that register. Decrement before you store the data, DB. Okay. So FD. Look at this table. So FD is corresponding to DB instruction. These two are the same instruction. These two. Okay, I'm trying to explain the meaning of that suffix DB and FD. Okay, then pop operation, right? So you backed up that data 1, 2, 3 to stack, and stack pointer is now pointing their location. Okay, after pushing 3 words, right? 3 words. So this location 3F8, 3F4, right? So stack pointer stores the data 3F4, okay, that location. After pushing 1, 2, 3, these 3 data to the stack. Okay, so pointing that location. So pop operation. I'm trying to explain which instruction is corresponding to FD. Okay, so that when you pop, you are loading, right? LDM load multiple. Okay, and R13 is pointing the location. You have to load that data. So which suffix do you have to use? Load multiple, increment, right? After loading, then you have to increment. Okay, increment address. So increment I after. Increment the register after accessing data. Okay, so LDMIA, that is corresponding to that instruction. So look at that table. FD is corresponding to IA. Okay, I'm trying to explain intuitively, right? So so then think about that for stack operation. If you use that instruction, STMDB and STMIA, then you have to think twice, right? So stack operation, push operation, okay, STMIDB first, DB, then do some data processing, okay, data processing. Afterwards, pop operation, then IA. So if you use those suffixes, then you have to think twice, okay? Decrement before. Stack pointer is pointing here, okay? So you are not supposed to push data to that location. Stack is not starting from here, one below, right? So you have to decrement before you push, okay? Then when you pop, you have to also think, a lot, right? IA, okay? The location is occupied by data. So that means what? That means I have to load this data first, then increment. So IA. So you have to think a lot. The assembly language is already complex. I don't want to think about this suffix. So instead, if you use this, suffix full stack, full descending, then that is more intuitive, right? So if you use FD, then at the end you use the same FD. Okay, so easy. That is so the programming, assembly programming would be the easier. Okay, with those instructions. And in high-level language, right? Compiler is using that stack by default, descending. Okay, descending, full descending stack. It's a full descending stack by default. Okay, high-level code. If you write C code, then it is using full descending stack. Okay, any question about this? Why is both push pop called descending? Yeah, just a name. Haechang, yeah, good question. Right? Why? Pop operation you are ascending, right? Address is incrementing, but it is from push operation perspective, right? Full descending, right? There is a stack, then location start from 0, okay? And when you push, stack is growing downwards. So we use that terminology from a push operation perspective, right? Stack is growing downwards, right? Just a terminology, yeah, Haechang, I think, yeah. Descending stack, as you push, stack is growing downwards. Address should be decremented. Stack pointer, right? Stack pointer should be decremented. As you push data, 0, right? Starting from here, push one data, decrement by 4, right? Decrement stack pointer by 4, then push data. Decrement stack pointer by 4, then push. Stack is growing this way. When you use other stack operation, when if you use, okay, Suho, a good question too. We typically use FD, okay, full descending stack. If you use high level language, then you have to follow that convention. High level language and assembly mix assembly code and high level language together. Then you have to use full descending stack. You cannot use empty ascending or other thing because C is assuming full descending stack. But if you use assembly only, and you can use anything you want, assembly only, right? So, Joan, if you use stack operation, do we have to write down? Yes. R13, STFD. Yes. I think ARM is providing pseudo code. Okay. So for example, here probably you can do this. Stack area. Okay. You reserve, okay, space. I want to reserve 1024 1024 words probably. Then that is 4 kilobyte, right? 124 multiplied by 4. Okay, stack area. Okay, then what you can do is, okay, stack area. Okay, so probably here, what? LDR. Okay, similar instruction, similar code, right? R13 or stack pointer. Okay, I want to initialize that to stack area like this. Then stack pointer initialized to that location. Okay, to make it full, then you have to do one add operation, I think. Right? Is it true? Confusing stack area. Okay, probably not. Okay, so here stack stack start. Confused. Stack start. Probably at the end, the stack end. Probably the last one. Stack. So initialize that to stack end. Okay, like this. Okay, then to push STM FD. Okay, stack like this. Then which register do you want to push? R02, R12, for example. Okay, so let me compile it. Okay. Okay, then check out this elf. Okay. First, label or symbol, right? So check out those symbols. Okay, stack start. Okay, that starts from that location A50. Okay, stack ends. Okay, E50. Okay, so A50, E50, A50, E50. So A to E. A10, E is what? 14, right? 400. So 400. Okay. So okay. So anyway, so that stack, okay, probably plus four, right? So okay. So if you write this code, then check out assembly main. Okay, that got translated to push operation. So SP is a stack pointer. So ARM is providing push instruction, I think, pseudo instruction. So instead of using STM, probably you can use in assembly, you can push like this. I want to push R0 to R12, okay, like this. So these two are supposed to be the same, I think. Check out the machine code. Okay, STM and push machine code, right? Same machine code, push and push. Okay, so if you use push instruction, pseudo instruction, then R13. Okay, compiler is using R13. Okay, as a base location because R13 is stack pointer register. Juan, does it? One more question. Can I use stack operation assembly to other stack operation to other register? Okay, you base location R0 or R1 as a base location. Like question is, okay, I don't want to use SP as a stack pointer. I want to use LDR R0 as a stack pointer. Yes, you can, but again, if you mix assembly and C together, then you have to be careful because C code by default is assuming R13 as a stack pointer. Okay. Probably the reason why you want to mix these two together, assembly is calling C, right? Probably C code, right? And after executing C, you are going to come back, right? So if you use this one, then this one is no longer true, right? So you cannot use that. So if you use LD STM FD, this is no longer pop operation, right? This one again, then R0 like this. Then compiler is not translating that into pop operation because R0 is not a stack pointer by default. Okay, so look at this. This one is STMTB, right? It is not stack pointer, right? So compiler is not using push or pop operation. If you change base register to other register. Okay. Any other questions? Okay, so again, stack is used all the time when you run C code. I think this C code, check out CSD main function name. This is a symbol, CSD main. So look at this. So when you make a function called this opening curly bracket, right? That got translated into push operation first. Okay, push some code. So it is adjusting stack pointer, okay, to make room for local variable. So you have local variable here. Okay, so reserve some area for local variable. Okay, so at the end, look at this, push and pop. Here, opening curly bracket, push, then closing curly bracket, right? Pop operation. Okay, push and pop. Okay, so when you push, so here, in this in the C code, you need to use those registers. Okay, probably in assembly code, you used this R4. In assembly code, you used R4, R5, and FP is I think R11. I think R11. Okay, so you want to make sure you back up those registers. Then you are free to use inside this function. You are free to use R4 and R5. Okay, because you already back up. Then when you return, you are popping that same R4, R5, and R11. Okay, push and pop operation. So stack is a super important operation that is used all the time when you run software. It's a function. Okay. Okay, that is about store multiple, load multiple operation. Okay, multiple data transfer. Okay, instructions. Now the last thing. Okay, swap operation. A swap instruction is very special instruction. Okay, so let's first read this one. Taeyeon, can you please?
Swap instruction. SWP swaps the contents of memory with the contents of a register. It is a special case of load store instruction. It performs a swap atomically, meaning that it does not release the bus until it is done with the read and the write. It is useful to implement semaphores and mutual exclusion with text in a noise.
Okay, swap instruction. It is a very special operation. Let me first explain the operation of swap. Okay, swap. That instruction is doing this operation. So animation before state and after state. Okay, so it is doing SWP swap R0, R1, then R2. So that instruction is reading from this square bracket memory location, right? So reading from that location and store into R0 register. That is equivalent to LDR, memory read instruction. Okay, memory read, load or memory read. Loading data from memory to register. Okay, and it is doing store operation. Okay, R1 will be stored. It is equivalent to str. Okay, store operation. So read and write operation. Swap. You are changing, right? Reading and their location. the data at that location will be overwritten with that value. So first this one, and second this one. Read first, okay? Then their location will be overwritten with the data. So read and write operation. Very special operation. And why? The question is, why do you need to do? Why you need to do this kind of operation? That instruction is provided to implement mutual exclusion in operating system. Mutual exclusion. What is mutual exclusion? A mutually exclusive operation. Think about the situation where many people are sharing one printer, and many people want to use that printer. When you submit the printing job, then the system, computer system, is checking if other people, other guys are using that printer or not, right? If the printer is being used by other guy, then you have to wait until that guy is done. That guy finishes his printing job, right? So one at a time, right? So that is called critical section in operating system, right? Critical section or critical shared resource, right? Shared. So when you access shared resource or when you access critical section is simply memory, area where some, so important data structure is stored. You want to manipulate this critical section, then you have to make sure no one is doing some operation with the data. Okay. So when you access, the best example is printer. Okay. So before you access printer, you have to make sure no one is using that printer. Then you can submit the job, right? Then how do you guarantee that mutual exclusion? That is typically implemented with lock variable in memory, right? In memory. Okay, so remove this. So some of you, I think some of you are taking operating system course, right? This semester. Okay, you will study that. Memory. So you have lock variable. That is typically initialized to 0. Zero means free. No one is using printer. Right? One is occupied. Someone is using printer, right? So locked or free or locked. Because I'm using printer. Okay. So before you use printer, you have to make sure that memory, the data is changed to 1. Okay, CPU. So lock variable. So mutual exclusion again, that is typically implemented with lock variable. So before you use a printer, you have to make sure you read lock variable. If there is 0, then you are free to use the printer. And before you use printer, that value, you have to change that value to 1, write operation. Okay, so read operation, read lock variable, and check if that is 0. 0 means free, right? No one is using printer, right? Then you store a 1 to this memory location to indicate, okay, I'm going to use that printer. Okay. Then other guy is checking this lock variable, and that is 1. So no one is going to send the printing job, right? So you acquire the lock. Okay, acquire the lock before accessing accessing shared resource or critical section. Okay, before accessing shared resource, printer, for example, printer, shared resource or critical section, acquire lock, acquire lock. And after you are done, okay, I'm done. I send my printing job, I'm done. Then you have to release the lock to change that to 0. Okay, acquire and release. And one more thing before explaining the purpose of that instruction. So probably you get some feeling, okay, you read and update, right? Read and update with one instruction. Okay. And then, what would be the problem if you use LDR instruction to read the lock variable and check the lock variable. Okay, so pseudocode LDR. Okay, so lock variable LDR store read from that memory location lock and store into here. Okay, then check out. Okay, if pseudocode, right? If R0 is equal to 0, then no one is using, right? Free. It is free. No one is using printer. Then what do you have to do? Okay, store. Let's say R1. So assume that 1 is already in R1 register. Okay, to lock location. Store 1 2. Store 1 2 here. Okay. Otherwise, the pseudo code, right? Some cheesy code. Otherwise, then what do you have to do? R0 is not 0, 1. Someone is being used. Printer is being used, right? By someone. Then you have to branch, okay? Some pseudo code, right? Branch, checking. Keep checking, probably checking here. Checking, right? You have to branch. Okay? Some pseudo code, some cheesy, right? Some cheesy branch code, right? Keep checking this. Okay, so what would be the problem with this code? So without that swap instruction, swap SWP, that code generates some problem. So what do you think? This one is something wrong with this code? Some pseudocode? This is pseudocode? So you have to think about, how your programs are scheduled in computer, in Windows environment or Linux environment or other small computer system, how programs are managed. If you open task manager, then at this point in time, this computer is running many different programs: Google Chrome, Logitech Capture, PowerPoint, remote desktop, some background processes, background programs. So look at this. There are so many programs are being executed in my computer now. So many programs. How those programs are being executed in computer? Operating system is scheduling tasks. Let me briefly explain. Probably you will learn about that in operating system course, but let me briefly explain. Time, and assume that you have 4 different programs you want to run. Okay, the first one is hello world. Okay, hello. Then music player, right? MP3 player, MP3 to listen to music. Then Chrome. Okay, Then at the same time, you want to cook up some documentation, HWP. Okay. So how that those 4 different tasks are managed? Operating system is doing context switch. For example, after executing hello world for 1 millisecond, that interval time, for example, 1 millisecond. 1 millisecond computer execute hello world. Then operating system says, okay, it is time to kick out and run new, program MP3. So that guy is kicked out. Okay, and then MP3 player kicks in. That is called context switch. You need to do context switch out that guy and switch in this one. Okay, then after 1 millisecond, after executing music player for 1 millisecond, and it is time to execute, the Chrome browser. I want to do the web surfing. Okay, so next 1 millisecond, right? Then it is time to do context switching, HWP. Okay, then after that, again, hello world. This hello world, resume hello world, and then after 1 millisecond, resume MP3 and so on. And this context switching is done so fast, every 1 millisecond. 1 millisecond, human does not recognize that small, time. So we feel like for human, right? We as a human, we feel like, okay, these 4 different programs are being executed at the same time because switching is done so fast. That is time multiplexed scheduling. So every 1 millisecond, you do context switching. Okay, so think about that. You have a single CPU. You have one CPU, then memory, right? That is your computer. One CPU, just one CPU. That CPU still able to execute these many different tasks, time multiplexed, manner. So that human has the illusion that these many different programs are being executed at the same time. Not actually at the same time. CPU, think about that, right? You have program counter, register file. Program counter is pointing the location where you read instruction from. So at certain point in time, CPU, computer, is able to execute only one program. Only one program, right? Program counter is pointing the location, right? Instruction is reading, right? But human, right? As a human, we illusion, right? We got illusion that these 4 are being executed at the same time because switching is done so fast. We cannot recognize that small time frame. So that got executed, after next 3 millisecond, right? So we feel like that is continuously executed, right? So that is time multiplexed scheduling, right? So in this case, assume that, so with time multiplexed scheduling in mind, right? So 2 people, okay? Here, Chanu, right? Chanu and Chaehyun, right? Chaehyun, printing job, okay? Chanu and Chaehyun want to send the printing job, HWP, to the printer, right? So Chanu want to check, this lock variable, okay? Using this code, and Chaehyun also want to, use a printer and make sure no one is using the printer by running this code, right? First check the printer is free or not. Then look at this. At this point in time, context switching time. Okay. So let's say after Chanu is reading Chanu is executing first code. Chanu, okay. So you reached this point, okay. So this time, Chanu's program got context switched out. Context switched. Okay, you time to kick out. I need to run Chaeyeon's program. Okay, so Chanu's program stopped here. It stopped here. Then what is the status? Okay, the status is lock variable is 0 initially. So Chanu, okay, R0 contains 0. Okay, R0 contains 0. Then got context switched. So Chaeyeon is running the same program, right? So lock variable is still 0. Okay, Chanu has not updated. Chanu has not executed that code yet. Okay, so Chaeyeon's program is checking this lock variable again, right? So R0 is still 0, right? Here R0 is 0. Here Chaeyeon's program R0 is 0. Then two guys think, okay, printer is free. So these two guys are sending printing job. So you have some conflict. Okay, mutual exclusion is not guaranteed. Does it make sense? Mutual exclusion, right? The thing is, in time multiplexed is scheduling, operating system stop the program. Okay, you don't know where, but we assume operating system stop Chanu's program. Okay, here after executing LDR instruction, then Chanu think, okay, printer is free. Okay, has not updated this lock variable yet because it stopped here. And Chaeyeon's program, right, reading from the same location, then end up having, end up reading, 0. So these two guys think, okay, printer is free. Okay, so we have conflict. Okay, so to prevent from that problem, prevent that problem from occurring, ARM is providing as swap instruction, SWP. So instead of using this code, you use SWP, swap. Okay, swap R0, R1, R, let's say lock variable. So read from the location, okay, and we assume 1 is already stored in R1 register, so store. That instruction, read operation, memory read operation, memory write operation. Okay, so these two operation is not separable. You cannot separate these two. It is atomic operation. We say it is atomically executed. Just one instruction. So you cannot separate these two. Okay, read. You cannot context switch. Okay, read is done. Okay, you stop. Then this one next. You cannot do that. Okay, it is atomic operation. Atomic. Okay, it cannot be breakable. Okay, so just one instruction. Okay, so you see the motivation why CPU is providing this kind of atomic instruction to support mutual exclusion. Mutual exclusion, right? So this one is an example. Look at this. What do you expect? Before and after state, right? So R1 contains 4 ones and 4 twos. Okay, R2 memory location is 9,000. So reading from 9,000 storing to R0. So R0 will have that value 1, 2, 3, 4, 5, 6, 7, 8. So then memory, right? You are storing R1 to that location. What is R1? This one. So after state, this one. So R0, okay, 1, 2, 3, 4, 5, 6, 7, 8. Then this value. Okay, any question about this? But okay, so one more thing. Single processor system, right? We got this problem. That is, ARM is providing this atomic instruction swap. Same problem happens in multiprocessor system. Think about you have two CPUs, CPU 0 and CPU 1, and memory. Okay, memory, and that is called the bus. Some connection to this memory. So CPU 0 can access memory through that connection. CPU 1 can use the same connection, same shared bus. Shared bus, meaning, the thing is here, for simplicity, I draw just one line, but here you have address and data and some control signal, address, data, control signal, same thing here. Okay. And the problem is, this one is a shared bus. These two guys are sharing this connection to access memory. Okay, so that means what? These two guys cannot access memory at the same time. Okay, at certain point in time, one CPU can access memory, and the other guy should wait until this guy is done, because shared bus. Okay, so then think about this code. CPU 0 is executing this code, and CPU 1 is executing this code. Okay, then CPU 0 executed this code, so R0 is 0. Then it is time for CPU 1 to access the memory, right? So lock is initially 0, so read 0 with that code. Then CPU 1, okay, CPU 1 is executing the same code, so R0 is 0. Then think, okay, these two guys think, okay, Chanu's code and Cheon's code, right? Two guys think, okay, printer is free. Now I can send printing job. You have a conflict. Okay, so to prevent that from happening, ARM is providing swap instruction, SWP. That instruction is not breakable. You cannot say atomic operation. So R0, R1, lock. Okay, so read operation and write operation. So read from read operation, this one, and write operation. So until you finish and read and write, system will guarantee, okay, you are using this shared medium. I can guarantee, okay, shared medium will be used until you are done with read and write. It is not breakable. Atomic operation. Does it make sense? Any question about this? Okay. Then unfortunately, right? Look at this. Swap instruction. Swap instruction is deprecated on version 7. Cortex A9 no longer support swap instruction. So if you try to SWP swap, right? R0, R1, then R2, for example. If you do this, some problem, right? Some problem here. Swap is deprecated. Swap is no longer supported in version 6 and version 7. Okay, then why did I explain swap instruction here? Because it is very intuitive, very easy to understand the problem, this mutual exclusion problem, and solution with the swap operation. That is why I explained swap instruction. Okay, but in ARM version 7, yes, good question, right? The reason is why swap instruction is deprecated because of the change in hardware structure. We no longer use, no longer. Sometimes we use that system hardware structure, but these days point to point connection. That guy. You are not using the same communication medium. Okay, this shared bus, some point to point connection, some different hardware structure. Okay, so that is why. So that is too deep to explain. Okay, so probably okay, so let me show you. Can I search ARM based hardware system? ARM based hardware system. Can I? ARM based SoC. Okay, so ARM based. It is hard to explain in short sentences. XC product connection based XC with XC. So shared interconnect, Cortex A9 shared interconnect. Okay, so so it is very hard to explain in one sentence. Let me think. Okay, so next time let me think and explain to you next time. Okay, but very good question. Okay, very good question. So instead of using SWP instruction, swap instruction, now version 7, version 7 is providing these two instructions. Okay, these two instructions for mutual exclusion, load exclusive, and store exclusive. You have to use these two instructions. Okay, so this is the one. So here, look at this. The two separate instruction. So load exclusive. Then R0 is the memory location, lock location. Okay, and read place into R1. You are checking R1 is equal to 0 or not. Okay, it is not free. Then you keep checking the lock. Okay, two different instructions. Then the log is free. If log is free, you force through. Okay, so R1 will be 1. Then store exclusive, meaning R1 will be stored to that location. and then you have to check R2 be a return value. If that operation, store operation is successful, then R2 will be I think 0. R2 will be 0. So compare 0 is equal to 0, equal, then you false, you are successful. You successfully acquired the lock. Okay, so using these two instructions, if you execute this code, then hardware is tagging. Okay, I don't want to explain in detail, but because they asked the question. So in hardware, you have a special module, okay, global monitor or local monitor. So if you execute that code, then that hardware module is recording the address information. Okay, someone is accessing that memory location. Okay, so the other guy is trying to access same location, then this guy failed. A little bit complicated. It is because hardware system is different, hardware structure is different. Okay, using global monitor or local monitor, hardware is checking, hardware is keep recording the location. Which location? This location. Okay. Okay, so the thing is, instead of using swap, you have to use these two instructions. Okay, there is the one. And one more instruction, clear exclusive. Thing is very little bit complicated. Actually, it is discussed in graduate level course. That load exclusive, and load exclusive, store exclusive, and clear exclusive. Why you need those instructions? That is discussed in graduation level course. So for now, I think swap instruction is enough. Again, the reason why I explain this one, because it is easy to understand the issue. Okay, why you need to swap? Why you need swap instruction? The problem and solution, right? So atomic operation. Okay, that is about ARM instructions, and then the remaining instructions, interrupt related instruction, okay, and CPSR manipulation instruction. That will be discussed later on. Okay, when we discuss interrupt, we will talk about SVC. Okay, so probably after midterm exam, we will talk about SVC. Then around that time, MSR instructions will be discussed. That instruction is for reading. MRS is reading CPSR, status register, to destination. Okay, MSR is doing opposite. Okay, so you are updating with that instruction. You can update. You can write something into that register. Actually, that is very dangerous operation. If you update this mode, then what? You are changing the operating mode, user mode to supervisor mode. Very dangerous operation. You have to be very careful. Okay, we will talk about that. Okay, when we discuss interrupt. Okay, that is about ARM instruction. Anything? Any other things you want to ask? Okay, from next class, we will talk about handling IO devices. Okay, if you check the schedule. Next time we are here, right? ARM instruction. We are almost done. Except SVC, the interrupt related, and CPSR manipulation instructions. Okay, so we are almost done. The next time we talk about memory map. Okay, that is very important topic to handle, to touch IO devices. Okay, so that will be discussed. Then we will play with some very simple, super simple IO devices. 3 IO devices. GPIO, general purpose, input, output module, then timer, and UART. These 3. Okay, very simple IO devices. Okay, then after that we will jump into interrupt or some other stuff, interrupt exception and so on. Okay, I think we have 4 minutes left, but I think this is a good place to stop. We don't have enough time to talk about stuff. Okay. So any question before letting you go?
질문 하나 해도 될까요?
Yes, please.
과제할 때 처음에 개발 환경이 좀 익숙하지 않아가지고 그런 부분에 대한 혹시 뭐 교수님 강의나 이런 게 있을 예정은 없나요?
I explained to you some demo right here, right? So during lecture, I gave you some demo, right? So try to analyze this example code. Okay, this example. So it's 성목, right? Try to understand, try to analyze this code. Okay, then play with that. You can download it. You can download it to the board like this. Download what? Download both hardware and software, right? So if you debug, then it is downloading hardware, right? Programming FPGA, programming this guy, and software goes to this main memory, right? So what you have to do is, check these registers and memory dump, right? Memory dump. So which location you have to, dump this location, source or destination. So in this specific example, you are copying this 16 data to, that location. That means you need to figure out the memory location of this source, right? And destination. That can be checked with ELP, right? Symbol table source. Here, look at this. SRC starts from that location. Okay. So 9E0. So 9E0, 9E0. Okay. So using this one, you can enter the memory location of your interest. Okay. Then how to execute the code? Simple, right? So you can press, look at this here, run F5, right? F5, then instruction by instruction execution. F5. Okay, one instruction, execute it and stop. So R0 register, change it to this one. So F5, R1 register, this one. So R2, F5, and so on. That is what you need to know. That's it. 성목. Okay, Juan, then do you have to know what there's some? Do we have to know that there are some instructions like LD? We don't have to know detail. Yes, for now, mutual exclusion. In this class, we are not going to implement mutual exclusion. Okay, Juan's question, right? So you don't have to worry too much about LDR EX and STR EX. Okay. Again, that is discussed in graduation level course, actual implementation with LDR, STR EX. Okay. Because you don't know for sure what do you mean by global monitor and local monitor, right? So address is a shared attribute, then physical address is marked as an exclusive access. Okay, so that means there is a hardware inside the hardware system. There is a module. So you run load exclusive, then module is recording that memory location. Okay, someone is trying to use that memory location exclusively. So other guy is trying to use same memory location with the load exclusive. Then this guy says, okay, someone is this module. Hardware module is saying, okay, you are not supposed to execute that. You are not supposed to access that location. Someone is, requested that memory location before. Okay, so some hardware, it is intertwined with hardware mechanism, hardware and software. So a little bit tricky and complicated to understand. But if you write operating system, if you are interested in writing operating system, not big operating system like Linux, Windows, that is huge, right? We are not talking about that huge operating system, but small operating system like real-time operating system, small. Then you have to understand LDR, EX, this one. But in this class, that is out of scope, too much detail. Okay, so we are not going to use that instruction in this class. Okay. Yeah, but good question. Today's question is super good. Yeah, and Juan, your question is good. Yes. Why you need that instruction instead of swap? Okay. So I have to think deep. I have to actually to explain with very clear, clear sentences. I think. Yeah, I have to think. Okay. Any other questions? Okay, I'll see you next time. Bye. Okay, thanks.